Hi, I'm Sam Jabley, and you're watching my Physics 2211 Lab 3 report for the Black Hole Lab. So, in this lab, the mass of a black hole is going to be calculated by analyzing the motion of a star orbiting the black hole. This will be done in a computational model. The mass of the black hole that was calculated will then be used to calculate the initial velocity that a spaceship will need to leave the planet it is on and fly close to the black hole without crashing into it. The purpose of this lab is to illustrate the relationship between Newton's second law and momentum, and to show that these two laws can be manipulated to find certain values. So, some details and results before we get into the lab. The system for part 1 is the star, and the system for part 2 is both the spaceship and the planet in their separate areas in an iteration. The star mass is 2 times 10 to the 30 kilograms, and the surroundings is everything that isn't the system. The computational model was made using GlowScript. And here are some results that I can preview here, but we'll see them again later. So, some background physics. Using Newton's second law, the formula for net force involving the perpendicular and parallel components can be derived using derivatives and the product rule. Then, rearranging the equation for the force of gravity between two objects, the mass of the black hole can be calculated in terms of the momentum of the star. So, my Model 1 code. I input the initial conditions here, mainly delta t, and then lines 130 through 144 show how the velocity will be calculated at each time interval. Then I computed the initial and final momentum vectors, and then used that to calculate delta v and delta p, and used that code to calculate dp dt, which is equal to F net. I then calculated the parallel and perpendicular components of the net force, and then I used the derived equation from previously discussed to calculate the mass of the black hole. And here's the results from this model. The mass of the black hole I got to be this number, and here you can see the F net and F net parallel and perpendicular components. So, Model 2 code, I inserted the mass of the black hole here, and then I changed the ship's speed and the X and Y components largely by trial and error until the model worked out. And then this big chunk of code, the purpose of this is to iterate and find the net force on the planet and the net force on the spaceship, and then you update the planet and ship velocity and position and do this again because it's a non-constant force that's occurring. And here's the results from Model 2. So, some possible errors. Outside forces were not considered in the model, so it likely does not represent reality. In reality, there's lots of asteroids and other bodies and other planets, and even other stars sometimes rotating in a galaxy. Trial and error was also used to find the initial velocity of the spaceship, so there's likely a velocity that would get the ship off the planet that is closer to the black hole without crashing into it. In addition, approximations accumulate through the iterations, which can lead to bigger errors. So, some discussion questions. What does it mean? Newton's second law states that mathematically the net force is equal to the rate of change in momentum, but the rate of change of momentum is easier to measure because the only thing you need is the velocity and change in motion of the system. And so for the what if question, to find the ship's speed in the X and Y, to see if it can orbit the black hole. This is what I got. I did this largely via trial and error, and as you can see, the magenta is the spaceship, and it would likely continue to follow this orbital path around the black hole. Thank you so much for watching, and I hope you learned something today.